Welcome, everyone. So today, we're going to break down the one thing that truly powers our modern world. I'm talking about the foundational component of all electronics. From the phone in your hand to the servers that run the internet, it all comes back to this one incredible type of material. All right, let's kick things off with a question about the very device you're probably using to watch this. What's that kind of magical material at its heart that's not a great conductor, but also not a perfect insulator? The answer, of course, is the semiconductor. And trust me, understanding it is the key to unlocking our entire digital world. So here's how we're going to tackle this. We're going to build our understanding from the ground up in 5 key steps. First, what a semiconductor actually is. Then we'll zoom way into the atomic level. From there, we'll figure out how we can actually control its behavior. And finally, see how we engineer it into the stuff that makes all our tech possible.
All right, first up, let's really nail down what makes this material so special. The amazing thing is, it's not about being the best at conducting electricity or the best at stopping it. No, it's all about being perfectly in between.
You know, a semiconductor is pretty much exactly what its name says it is. It doesn't let electricity flow freely like a piece of copper, but it's also not a total roadblock like glass. It's the Goldilocks of materials. Its conductivity is just right for us to get in there and manipulate it.
Now this table right here shows us something absolutely incredible. Resistivity, it's just a measure of how much material pushes back against electricity. Now look at these numbers. Copper's is teeny tiny. Electricity just zips right through. Then you have glass with a number that is just astronomically huge. It stops electricity cold. And sitting right there in that perfect sweet spot in the middle, that's germanium, a classic semiconductor. This enormous range, this massive difference, is the secret to why we can control them so well.
Okay, so let's zoom in. Let's go down to the atomic level and see how this unique behavior is actually born from the way its atoms connect to each other. The whole secret is in a very stable and, well, a very particular kind of bond.
Everything, and I mean everything, comes down to this one magic number, 4. See, atoms like silicon and germanium, the stars of our show, they have exactly 4 electrons in their outermost shell. These are called valence electrons, and they are the key to building the perfect, stable structure that we need.
Because each atom has those 4 electrons, it can form 4 incredibly strong covalent bonds. It does this by sharing 1 electron with each of its 4 neighbors. You can picture it like an intricate and perfectly repeating atomic handshake, holding everything together in a stable crystal.
So if these bonds are so strong and they're holding all the electrons tightly in place, how do we get any electricity to flow at all? Well, the first and most basic answer is pretty simple. We just add a little energy in the form of heat.
And this illustrates that point perfectly. At absolute zero, as cold as it gets, those bonds are basically unbreakable. The material is a perfect insulator. But as you warm it up even a little bit, that thermal energy can be just enough to knock an electron loose from its bond, freeing it up to move around. Okay, now here's where it gets a little bit wild. When that negative electron leaves, it creates a vacancy, right? Think of it like an empty parking spot in the atomic structure. We call this a hole. And because it's a spot where a negative charge should be, the hole itself actually behaves like it's a movable positive charge. Kinda cool, right? And this is a fundamental rule you gotta remember. Thermal energy always creates these electron-hole pairs together. An electron pops free, and a hole is left behind. The only problem is, even at room temperature, the electric current you get this way is way, way too small to be useful. We need more control than that.
And this brings us to the real climax of our story. If just heating a pure semiconductor isn't going to cut it, we need a better, more deliberate way to control its conductivity. And the method? Well, it's a stroke of absolute genius. The solution is a process called doping. And yeah, it sounds a little illicit, but in electronics, it's the art of intentionally introducing tiny, precise amounts of impurities into that pure semiconductor crystal. We're essentially hacking the material at an atomic level to give it the exact properties we want. The process, in concept, is actually pretty simple. You start with a pure, or what we call an intrinsic semiconductor. Then you add a very specific type of impurity. This transforms it into an engineered or extrinsic semiconductor, creating one of 2 incredibly powerful new types. And these are the foundation for all of our devices. So let's see how this whole doping thing creates the 2 fundamental types of semiconductors we use. It all comes down to a really simple choice. Do we add an impurity that has 1 more valence electron or 1 less?
So, let's start by adding an impurity that has 5 valence electrons. That's one more than our germanium's 4. A classic example here is arsenic, and we call this a pentavalent impurity.
So what happens is the arsenic atom slides right into the crystal structure. 4 of its 5 valence electrons form that perfect atomic handshake with the germanium atoms around it. But what about that 5th electron? It has nowhere to go. It's just left over, untethered, and totally free to move around and act as a negative charge carrier. This is what creates an N-type semiconductor, with the N standing for, you guessed it, negative.
Okay, now let's completely flip the script. What if we add an impurity that has only 3 valence electrons, something like gallium? We call this a trivalent impurity.
So again, the gallium atom fits in just fine. Its 3 electrons form 3 of those covalent bonds. But for that 4th bond, there's a problem. The gallium atom doesn't have an electron to share. This creates an incomplete bond, which is that exact same empty parking spot we talked about earlier. It creates a hole, which acts as a positive charge carrier. And this gives us a p-type semiconductor, with the p standing for positive.
So here's the big takeaway. Doping gives us this incredible, precise control. By adding a pentavalent impurity, we get a material that's swimming in free electrons. By adding a trivalent impurity, we get a material that's full of holes. We can literally custom tailor the electrical properties of the material on demand. This right here, this is the breakthrough that allows us to build complex circuits.
And that leaves us with one final and really fascinating question. We've just engineered these 2 custom complementary materials. One has an excess of negative charges, the other has an excess of positive charges. So, what do you think happens when we bring them together, when we join them side by side? Well, the answer to that question, that's the gateway to understanding diodes, transistors, and, well, all of modern electronics.